So, like I said, we've got a couple lessons left of new material. So, kind of like at the end of every unit we really had, the last step is, can we write our own equations? So, day 1 of writing equations will be today. Day 2 will be tomorrow. And we're going to talk about how to go from just, hey, here are your roots, to all the way to a fully formed equation. Right? X to the third minus 4x squared plus 3x minus 20, something like that, right? How do you go all the way from roots to that, okay? And you started a little bit on your homework with that, with a couple questions that were like, here are some roots, what would the equation be? But those were easy roots. We're going to talk about when it's a little harder, okay? So in order to do that, got a couple warm-ups that will kind of roll us right in, okay? So here's what we have. We have 2 equations that we need to solve, meaning we need to find the roots, we need to find the zeros, we need to find the x-intercepts if they are x-intercepts. And we know that one of them goes with the graph, and that's useful because the graph has a root on it, so that'll help us with that one. Now, how do we know which one? There's a few ways we could know. But how do we know which one of these equations we could use the graph with to help us? There's a couple things that will give it away. What do we think? Yeah?
The first one, because...
You think it's the first one? Go ahead.
Because 5 is a factor of 35.
So 5 could multiply out to get you 35, whereas it couldn't to get you 12. Yeah. Good. What else? Yeah?
I think it's the second one because you can factor...
Wait, which is the second one? Which is the second one? The one that you're saying, what are you saying about it? That you can factor it?
Yeah.
Okay, so you're agreeing. So we were saying which one goes with the graph. So the first one goes with the graph. The second one is what you're, yeah. So we were agreeing. Yeah, because that's the other way you could tell is, hey, you could factor this one. And I said one could factor, one goes with the graph. Okay? There's one other way. Anybody? There's something in each equation that you can see on a graph. Yeah? Well, they're both cubed. But yeah, the y-intercept, right? So this one is 35. This one's 12. How does that help us? Yeah, so this could be a y-intercept of 35. Yes, I know it's 1, 2, 3, 4, 5, 6, 7. But if you assume that each one is 5, then that could be true. Whereas with 12, 7 doesn't go into 12. So it wouldn't really work for that. Yeah.
Sorry, my brain's just getting confused.
So each square the scale is what's confusing. Each square going up is worth 5, right? So you would have to make that assumption, but you could confirm it with the other pieces that we talked about. Yeah. So, okay, if we know this one goes with this graph, how does that help us? Because we're trying to solve. How does that help us solve? Yeah.
We already know a group that we can do synthetic division for.
Perfect. Yeah. So we're trying to factor this, right, in order to solve. Well, first of all, if we're solving, we're setting it equal to 0. And then we're trying to factor it, but it's not factorable in the tricks that we've learned, in the grouping, in the quadratic form, like all those things, right? So we talked about using synthetic division. So one thing that we talked about last class is, well, if you don't know a root, I guess you could just start guessing. But if you're given one, that's really valuable. Why? Like if I know I have a root of, what is it? -5. What else do I know? Yes, I have a factor of x plus 5, which means that this is actually 0 equals x plus 5 times something. That's what a factor is, right? So how do we find the something? By doing synthetic division. I divide this by this, and I'll get this, right? So synthetic division, -5 on the outside. And I do 1, 2, -8, 35. And what do I expect to get? As my remainder, I should say. 0, because I saw on the graph that it's a root, so it's got to be a remainder of 0. unless something went wrong here, right? Okay, so I bring down the 1, multiply, minus 5, add, minus 3, multiply, 15, add 7, multiply, minus 35, add 0. Good. Minus 8 and 15. Yep. Okay, so we got 0, but we kind of knew we were going to get 0. That's not the important part. What did we find? Why did we do this? Yeah.
We found the missing bit.
Yes. So this part right here is the other piece, right? Which is?
What? It's x squared minus 3x plus 7.
Good. Okay. So let me write this down here so we can keep going. 0 equals x plus 5 times x squared minus 3x plus 7. Okay, so I want to try to keep factoring this because I want to be able to use the zero product property as easily as possible, right? So in the hopes that I can continue to factor this, I do what? Yeah, I try magic x, and I go, okay, 7 and minus 3. And then I say, okay, what multiplies to give me 7 and adds to give me negative 3? Nothing. Oh, man. Nope. It's not going to work. Now, if I was really tuned in on what we've been doing, I would have known that wasn't going to work. How?
Because it's 7's factor into.
Not even about the numbers. What do you think?
I was going to say because 7's a prime number.
Well, that's good. But I'm talking about, what do I know about polynomials that told me I was never going to get a magic x situation? Yeah.
On the graph, it's the imaginary root since it doesn't touch.
Yep. So look at the graph. How many roots did we get? 1. And it's real or imaginary? Real. And we know that it's cubic. We know there should be 3. What do we know the other 2 must be? They have to be imaginary. There's no other x-intercepts. Do we ever get imaginary numbers from magic x? No. What are the only times we've ever come up with imaginary numbers from when we're solving? The quadratic formula, right? That's the only way to get it. You square root a negative and you're like, okay. Or I guess you could get it from isolating the square. Okay? So, knowing that, I could have just jumped right to saying, hey, this is fully factored. I can't factor it further. Whenever you are fully factored, what's your next step?
Quadratic.
Well, before that, what allows us to do the quadratic formula?
Check to see.
I have 2 things that are multiplying to give me 0. Therefore,
Zero product.
the zero product property says, hey, let me make some easier equations for me. X plus 5 equals 0, and x squared minus 3x plus 7 equals 0. All right, so, and I've said this before, whenever you're doing these problems, you always kind of want to, every step, pretend it's a new problem. Pretend, hey, what if the teacher just gave me this to start? What would I do, right? Because it kind of resets your strategy brains, right? And then you're like, well, this one would be really nice to my teacher. X plus 5 equals 0. I could just minus 5 from both sides, and I get x equals negative 5. Right? And this one, if my teacher just gave me this problem to start, well, I'd think back to the quadratics unit, and I'd think about how you solve when you can't factor a quadratic. And I remember, oh yeah, that's when we, what? Use the quadratic formula, right? So that's hopefully where your brain goes, right? You go x equals negative b, so 3 plus or minus the square root of negative 3 squared minus 4 times 1 times 7 all over 2 times 1. And you don't need to memorize that. Formula's right there, right? It's got to plug in your a, b, and c. What you end up with is x equals 3 plus or minus the square root of, all of that becomes negative 19, and then 2 times 1 is 2. Now we're pretty close, right? Because 19 is a prime number. You can't break it down. But I never leave a negative under a square root, right? What do I do instead? You pull out the square root of negative 1, which we call I. So my answer here is x equals 3 plus or minus I square root of 19 over 2. Okay, how many roots did I find? 3. 2 are imaginary, right? That makes sense because we knew we had a cubic function and we had one x-intercept, so it kind of confirms what we had in mind, right? 3 plus or minus I square root of 19 over 2. Okay, so that was your first one, right? And we got 2 imaginary answers, okay? All right, this one I said you could factor. So if I have this situation, you got to think back to our factoring strategies. If I have a 3, 2, 1, nothing situation, grouping, right? So I'm going to turn these into 2 groups, and I'm going to GCF each group, right? And I'll set it equal to 0 all at the same time. So this first group, what goes into both? X squared, and then that leaves me with x minus 4. This group, minus 3, leaves me with x minus 4. And this is the part we always get tripped up at, right? What do I do now? The thing that shows up twice goes out front. Everything else goes in the back. In other words, we GCF the x minus 4. Okay, so x minus 4 and x squared minus 3.
I have a question. What if we did like x squared minus 3?
X plus 4? That's fine.
Minus 4.
Yeah. Oh, I'm sorry, yeah, x minus 4? Yeah, that's fine.
Oh, yeah.
Totally fine. Order doesn't matter. Now, can I factor further? Because I always got to check if I can. No, I can't, because I don't have a difference of squares. I just have x squared and minus 3. And the other one's just a binomial with a single x. Okay, so I can do what? Yeah, time that when you can't factor further, your brain should always go, okay, I guess it's time for zero product property. X minus 4 equals 0, and x squared minus 3 equals 0. Add 4 at both sides, I get x equals 4. Here, what would I do? Close. Add 3. I'd get x squared equals 3, and I would get
X equals the square root of 3.
square root, and I'd get x equals what?
The square root
Plus or minus the square root of 3. And why? Why is it not just the square root of 3? No, but why isn't it just plus the square root of 3? Why is it plus or minus the square root of 3? Let's remind ourselves why we do that.
Because the x minus 4 is only one root, and the only possibility
It has to have 3 roots.
it has to have 3 roots.
It's a good way to confirm we did the right thing, but let's think deeper. Why every time we square a root do we end up with a plus or minus?
Because there's 2 possibilities, because if it's a negative
Mm-hmm.
number times a negative number, you still get a positive answer, and if it's a
Good.
positive,
Yeah, so if you think all the way back to like square root of 9, well, let's not do that because we already have a 3 involved here. Let's go with square root of 4, right? When I first threw that at you, everybody said 2. And I said, it's not just 2.
it's plus or minus.
It's plus or minus 2. Why?
Because if you do negative 2 times negative
Because negative 2 times negative 2 is also 4, right? So we account for both possibilities. Okay, now that takes us into what we're going to do today, okay? And a key takeaway, something maybe we noticed but we need to define and talk about now, okay? If I have this situation and then I also had that situation, what do they have in common? What do both of our solutions have in common? Couple things, right? Well, they're different problems, but what happened in both situations? Yeah.
You ended up with 2 imaginary solutions.
Well, be careful. Are those imaginary? If there's no I, it's not imaginary. Think of how many real roots do I? Well, let's pause there. That's an important point because I should have clarified that. How many real roots do I have in the second one?
Oh, second one? 3.
3. Does that make sense? Square root of 3 is a real number. If you put square root of 3 into your calculator, you'll get an answer. It'll be like 1 point something forever, right? So that's a number, that's a real number, that's an x-intercept, like that'll happen, right? So don't assume it's imaginary just because we square root it, right? Now, we did have something that happened in both, though. What happened in both?
There's only one single.
I'll be more specific. There's an action we took in both, and there's a result that happened in both that they have in common.
There's one single and one double. And that's the one.
Well, be careful with the word double. It's not like I got a double root would be like 2 and 2. I didn't get that, right? It's not a double root. Yeah. We square rooted both times.
Oh, yeah.
And every time we square root, we have a result that involves a what? A plus or minus, right? So is it ever possible to get just a plus I?
Yes.
This is an important point. So if we're a little dazed here, I would lock back in for a second. Is it possible to get one just positive I as your result? No, why not? But why? Because it's great to remember that, but it's better to remember why. Yeah.
Would it be because just plus I would be a real number?
No, I is imaginary. But if you think about it this way, what's the only reason you ever get I? Why did we come up with I in the first place? There's a negative under a square root, right? That's what makes an I. And every time we square root, we plus or minus. So it's literally impossible to get an I without a square root. So that means there's always going to be a minus to the plus, right? So if you remember that, you'll never leave it out. Now, what about the other one?
Plus or minus.
We can't get a normal radical.
We can't get rid of the radical, right? And we also got a plus or minus. So anytime we square root, we end up with a plus or minus. Well, if I have a radical, I clearly square rooted. If I have an I clearly square rooted, right? Which brings us to the main takeaway that we need to add to our understanding here, or at least maybe not our understanding, but our toolbox, I should say. All right, so let's actually keep moving forward, and we'll come back to homework questions. Okay, so let's define these two pieces. Okay, so these are two types of roots, irrational roots and imaginary roots. And they have something in common, something that happens with them every time, and knowing that provides us information, and it allows us to keep going when maybe we couldn't before. Okay? The word irrational. Think about the word irrational. What's an irrational person like?
They're not realistic.
They're not realistic because they're not being rational. The means not. So irrational means not rational. Well, an irrational number is not a what number? A rational number. A rational number is what?
The number that is true?
Well,
Wait, no.
it's in the word rational. What word is in there? Ratio. A rational number is literally a number that can be described as a ratio. So that's either a fraction, like 4/3, or a whole number, like 2, because you could say 2 over 1. So that's what a rational number is. Irrational numbers cannot be described in that way. They would just be decimals forever. So we leave them under the square root. Okay? So that's an irrational number. Imaginary numbers, we know, right? They involve that I. So, but let's write that down. So irrational roots are essentially roots with a square root in them, right? And imaginary numbers are roots with a I in them, right? So those are your two things that you can look for. Oh, I have an irrational root. Oh, I have an imaginary root. And then once you know I have one of those types of roots, and this was what the warm-up discussion was kind of about, what else do you know? Both always what? Well, we kind of can just put I without the square root, but you're right, square rooting happens, and therefore Well, the rational ones do. The imaginaries don't. But what do they have in common? They're always
Plus or minus.
plus or minus. They always come in plus or minus pairs, right? So you should never, ever, ever just get one imaginary answer or one rational number. It really helps you if you are looking for that missing root, right? Because if you're like, oh, I got 2, where's the other one? Oh, one of them's irrational. Therefore, I must have missed the negative, right? So they both always come in plus or minus pairs, right? It's literally the same thing with a plus or minus in front of it, okay? So we'll talk about a little bit more why that's useful. We'll give you some examples, right? If you have square root of 5, you also have what? Like if I have positive square root of 5, I also have minus square root of 5. If I have negative 4i, I also must have positive 4i. If I have 1 minus 3i, what else do I have? 1 plus 3i, right? Because that's where the plus or minus would have went, okay? And you could say the same thing here. If I have 2 plus square root of 2, I have 2 minus square root of 2, right? Okay, so why is that useful? Let's start talking about it. And you're going to do a little bit of work on your own here. I'll get you started. We're going to find some missing roots. So we're going to pretend somebody is asking us to make a function, right? And they're being a little coy. They're like, I'm going to give you 2 of the 3, and you have to know the other one, right? So we know there's a missing root, or more than one missing root. Okay, so a couple things you got to think about. How many roots should we expect? What's given and what's missing? So for instance, if you have a cubic function, how many roots do you expect? 3. So I'm looking for 3 roots. And then we're going to talk about, well, what did they give us and what's missing? So they say there's one real root at 3 and another real root at square root of 7. Okay, so we're given 3 and square root of 7. But we know, not even just because it's cubic, but because what we just learned, that there has to be a missing root, because that's impossible, right? You can't just have 3 and square root of 7. You must also have negative square root of 7. Okay? I'll do one more and then you can do the other 2. Okay. Quartic function has how many roots? 4, right? And it says we were given some information. Double root at 2, imaginary root at negative 7. So what roots do we know?
There are 2, 2.
Yep, there's a double root at 2, so that's 2 and 2 again, both positive, and negative 7i. And we knew we needed 4, so we are missing plus 7i. Okay, you do the other 2. Go for it. All right, so cubic function, how many roots? Back to the front. 3. And I know I have a root at 0 and a root at 1 plus square root of 11. So missing must be what? If I have 1 plus square root of 11, I must also have 1 minus square root of 11. This is a quartic, so it's got 4. And I'm given 2. So we're given a root of 2 minus I and 2 square root of 2. So how many am I missing? 2. Okay. 2 plus I, good. And then minus 2 square root of 2. Good. All right, sounds like we're solid on that concept, right? Okay, so let's go to the back. Now, for the back, this is just a little skill check to make sure that we are solid on how to do these things because we're going to need them for what we're about to do. Okay. First, just a little practice with square rooting b squared minus 4ac. This would become 100, and then it would be minus 4 times minus 2 times minus 8.
64 minus
minus 64, right? Just do those one at a time. This times this times this. Don't try to do it all at once. And that's square root of 36, which is plus or minus 6. Right? Now, this one's a little tricky, or not. You could just remember when you have the square root of something times itself, it's what? Yeah. Question? Okay. When you have the square root of 3 times the square root of 3, it's just what? Anybody know?
Square root of 1?
No. It's just, when you have the square root of something times itself, it's just the number underneath. This is just 3. So you can just remember that. All right? You can just remember that, or you can actually do the math. You can say, okay, well, this is the square root of 3 squared, and those cancel, square root and the square, and you just have 3. Okay? Make sense? Any questions there?
No.
Yeah.
What would happen if there were two different numbers and you were multiplying?
Well, you could, anytime you have a square root of, like if I had square root of 2 times the square root of 6, you can just bring those together and say that's the square root of 12. Right? So this would become the square root of what? What's 3 times 3? 9, which is 3. Right? And you might think, well, what about the plus or minus? Well, the minus 3 would not be able to get you back to square root of 3 times square root of 3. So we leave the minus off. But don't worry about that. Just remember the rule. Square root of 3 times square root of 3 is 3. So that's what we got. It's going to come up. So just make sure you remember that. You'll be golden. Just square root of something times square root of the same thing as the number underneath. Okay. And this one, okay, so this seems to trip people up because they think of I as its own thing, but it's just a variable like anything else. It stands in for something else, right? If this said 3x times negative 3x, what would we say that is? Negative 9x squared, right? Well, it doesn't say x, it says I. So same thing, negative 9I squared. Now the extra piece here is you need to know what I squared is.
1.
It's negative 1, right? That's something you just want to remember. I squared is negative 1. If I see I squared, I'm replacing it with a negative 1. So it's negative 9 times negative 1 equals 9. Okay? By the way, why? Why is I squared negative 1? Right. I equals the square root of negative 1. I squared equals the square root of negative 1 squared. What did we just talk about, right? It's just the number underneath. Yeah, your question?
What happens when I is cubed or put to the fourth power?
Great question. Any honor students want to answer? Because they had to go that far.
Would the negative I cubed would be negative.
So let's do it. We got time. I cubed, right, would be I squared times I, right? Well, what do we just say I squared is?
1.
Negative 1, right? So this is negative 1 times I, or negative I. I to the fourth, watch this. It's I squared times I squared. What do we just say I squared is? So it's negative 1 times negative 1, which is positive 1, right? What do you think happens at I to the fifth? It flips right back to I. Because I to the fifth is I to the fourth times I. We just said I to the fourth is 1. So it's 1 times I, so it's just I, and then it just cycles from there. Okay, you don't need to, that's just interesting. Good question. All right, you don't need to know any of that if you weren't in honors, but it's good to know. All right, okay, so now we practice those skills. Why? Because we're going to need them. Okay, so we're going to do a couple problems, and then we will be working on our merry way. Okay, so there was a problem on the homework that was kind of like this, where I was like, here are your roots, write a function. So if that didn't make a ton of sense, this is the time to learn it, and you're going to learn with a harder version of it, okay? So a cubic function has a root of negative 3 and an irrational root of negative square root of 11. Okay, it's asking us to write in standard form. Now, what is standard form? It's almost easier to remember what standard form is not. Standard form is not factored form. Factored form is how we get to standard form a lot of the time. Like, for instance, remember with the quadratic, that's standard form. Ax squared plus bx plus c. It's just not factored, right? So if they're asking for this in not factored form, that's where we need to end up. So, for example, x to the third plus 2x squared minus 4x plus 20, something like that, right? That's where we want to get to. And all they're giving us is two roots. Question?
If we get ax cubed and everything, it's also standard?
Yeah, so standard form, that's the standard form of a quadratic, but there's a standard cube, there's a standard...
a cubed or a like to the fourth, what's a, b, c? Which one?
It doesn't work the same way. There's not an A, B, C like that. There's a C and there's an A, but we don't use B for the middle stuff because there's a lot of B. Okay, so let's go through the process, and this is the process I think is most helpful for students. So if you want to just verbatim go with what I go for here, because it's kind of a logical. What do we have? What do we need to know? Okay, so we start out by saying what we know. Cubic function. So what does that tell me? 3 roots. And then I list the roots. Well, they told me 2. What did they tell me?
Negative
3
3.
and
Negative
negative square
square 11.
root of 11. Okay, but they told me that it's cubic, so what else must be there? And also, what do I know has to be there, because this is impossible to just be like this? Has to be positive square root of 11, because there's no way you would get a square root that was just negative or positive. It would always be a plus or minus. So, okay, there's my 3 roots, so I'm on my way. Okay, how is that helpful? Well, if we know roots, we know factors. Okay, so let's pause and talk about how to get from a root to a factor. Because it's one of those things where I feel like we learned why, and then we just remembered that it happens every time, and then we just flip signs, and then we don't remember actually what we're doing. Okay? If I have a root, let's say I have a root of 2, what's the factor? It's not negative 2, it's x minus 2, right? X minus 2. Okay, so what did we just do? We didn't switch signs. That's not all we did. Yes, we switched signs, but that's not all we did. We had, let's say, root r, and we changed it to
Factor form, which would mean it would be x minus r.
right. So we take the root, and then we go x minus the root, and that gives us our factor. There's a reason for that, because we're trying to get 0 to get an x-intercept, and 2 minus 2 gives you 0. R minus r gives you 0.
Isn't it because of the distribute when you distribute to both sides?
It's related to the zero product property. It's basically, x-intercepts have an output of 0, right? So we need this quantity to be 0. Well, 2 minus 2 is 0. R minus r is 0, right? That's why we do x minus the root. Now, it's pretty easy when we have a number, right? For instance, if we're trying to find our factors here, well, if I have minus 3 as my root, what's my factor? It's x plus 3, right? And we just jump to that. But why? Well, think about what we just did. It is x minus the root. What's the root? Minus 3. What is minus minus 3? What's a minus minus become? Positive. And that's why it becomes x plus 3. Now, do we need to do that every single time? No, but it's helpful when we get these weird ones, right? That we've never had to turn into factors before. Like, for instance, oops. If I wanted to just do the same process, turn this into a factor, I would go x minus, and then what? Minus square root of 11. So the factor that goes with that is x plus square root of 11, which I know is a weird looking factor, right? But we're going to use it for now, okay? And then if I have plus square root of 11, I would just say x minus the square root of 11, and I'd be done. And these are my three factors now. Okay, so we took what we knew roots, we turned them into factors. Remember, we want standard form, right, which we can't get to right away, but we can get a form. What form can we do right now? If I knew all three factors, I can do factored form, right? So let's start there. We'll start in factored form, okay? So I would say, okay, f of x equals, remember what factors are? They're just things that multiply to give you the bigger thing. So if we list them all out and we multiply them to get the bigger thing, we'll be good, okay? So write them in a row, okay? So let's see, x plus 3, x plus square root of 11, x minus square root of 11. Great, so we're in factored form, but it asks for standard form. How do I go from this to the fully standard form version of this? Yeah, I got to multiply it out. Remember, factors are things that multiply to give you the bigger thing. Let's multiply to get the bigger thing, right? Now, remember when we did multiplying of polynomials, I compared it to something like this. If you had 2 times 3 times 4, and you had to do that math, in your head, would you go 2 times 3 times 4?
No, 2 times 3 times.
You do 2 times 3, you'd be like, what's that? 6. Okay, 6 times 4, like you pause, you get an answer, and then you keep going, okay? Same deal, except here, I kind of want to do the 3 times 4 first. I want to do this times this, because this looks like the easy thing to do at the end. These look like they go together. So I'm going to do the weird ones first, right? Just like I could have done 3 times 4 is 12, 12 times 2 is 24, and got the same answer.
But okay.
It's going to work out way easier. And if you want, you can write these first to make yourself feel better. Put the x plus 3 at the end. Okay? But look, it works. 2 times 3, it would be 6 times 4. Come on. 6 times 4, which is 24. But if instead I did the second 2, I did 2 times 12, I still get 24.
Yeah.
Right? So it's okay to do. And it's going to be easier because you'll see what happens here. There's some things that just cancel out and go away and make our lives easier. If we try to do this times this first, that won't happen. So it's still possible, but it's just, trust me on this one. Okay, so I'm going to FOIL these two and leave this one alone. So this one's just going to come down, and I'm going to FOIL here. I know some people like box. I'll give you box in a second because we're not done with this problem yet. All right, so first is x squared. Outer is minus square root of 11 times x. Inner is plus square root of 11 times x. And last, okay, so I have positive square root of 11 times square root of negative square root of 11. We just said a square root of something times the same square root is just what? Well, no. Think about square root of 3 times square root of 3. It was just what? 3. So square root of 11 times square root of 11 is just 11. Okay, now we'll think about the signs. So we have 11, and then I had a positive times a negative.
That would mean it would be negative.
So it's negative 11. Okay? So this times this is always going to give you that negative of the number underneath. Now, this looks crazy, but what happens? Anybody know? Like, this looks like a whole mess. It's negative square root of 11 times x, positive. Yeah. If you had minus 3x plus 3x, what would you do? How many x's would you have? Negative 3x plus 3x. It's 0 x's, right? So if you have a negative and a positive, the same thing, they go away, right? So these will cancel every time. And that's why we do this one times this one. So we can get that cancel. Okay, so what do I end up with? I have x plus 3 times x squared minus 11. I can do that. That's not bad, right? So now, for you box enthusiasts out there, I'll have x plus 3 and x squared minus 11. Another way to do FOIL, right? And I do each box one at a time. X to the third plus 3x squared minus 11x minus 33. Now, the one thing I will say here is I always told you that the diagonals will typically be like terms that you can combine. The reason I always said typically, because this is a situation where they're not, right? You're not always going to have like terms. You need to be very careful. So what's the biggest thing we see here? Highest degree? X to the third, no like term. Then what else do we see?
X squared.
3x squared, no like term. What else? What's the next one?
11x.
Minus 11x. And then minus 33. So there didn't turn out to be any like terms, and that's okay. We just list everything, right? And, whoa, that was cool. This is our standard form equation. Now think about what we were able to do there. Someone gave me two roots. One of them was irrational. I was just able to take that all the way to a standard form equation, right? If I put this into Desmos, what do you think the x-intercepts would be? Yep, -3, negative square root 11, positive square root 11, right? We have come all the way here. We're at the end of the unit. We are able to write our own functions. Question?
After that, we don't group anymore.
No, grouping is when we're trying to solve and factor and find roots. They started with the roots, and we're going the other way. We're trying to get to the, it's almost like they gave us the answer to the question, and we're trying to find the question. Okay? All right, so last question, same process, but with imaginary roots. Okay? So I'm going to let you try it. Okay? Think about how many roots you have. Think about which ones are given, which ones might be missing, how to turn them into factors, and then multiply it out. Okay? And then we'll go over it, and then we'll be done. All right. All right. All right, so let's go over this. Okay. So we got a quartic function, right? It's got a double root at -1 and imaginary roots at, or a imaginary root at 5i. And we'll deduct what else it must have, right? So my roots, how many are there? 4, good. You don't want to miss any. And I have a double root at -1. So what do I know? How many do I know from there? 2, right? I got -1 and -1. What other root did they give me? 5i. And if you want, you can write positive 5i, because that'll remind you what? What else do I need? You have it written right there. -5i, good. Okay, so those are my 4 roots, right? But I kind of want factors. And I said, go from root to a factor, you just do what? X minus the root, right? So my factors are x plus 1, x plus 1, x minus 5i, and x plus 5i. Great, so I have my factors, right? Now I write in factored form, which means I write them all multiplying by each other. So I say, okay, f of x equals x plus 1 times x plus 1 times x minus 5i times x plus 5i. Okay, well, the last one we had 3 things being multiplied. Now we have 4, but the same thing applies. Just do a couple at a time. What I would suggest, and you don't have to do it this way, you could just go left to right, but I would say do the normal ones, normal looking ones together, do the weird looking ones together, and then bring those 2 together afterwards, okay? So what does that look like? Well, we would FOIL this, right, or box it, and just in the interest of time, I'm going to tell you what it would be. It would be x squared plus 2x plus 1. That's what you would get, right? This one I'll do out with you, right? So if I FOILed this, well, x times x, that's x squared. Outer plus 5ix. Inner minus 5ix. Which, of course, looks crazy, but it's okay because it's going to go away. And then minus 5i times 5i would be minus 25i squared. Okay, so this looks crazy, but it doesn't matter because it's a plus and minus of the same thing, so it cancels, right? So what I end up with is f of x equals x squared. So there's only 4 minutes left, so can you wait, please? X squared plus, plus 2x plus 1. And then over here, I have x squared, and then I have minus 25 times I squared. What do we know I squared is? Negative 1. So that's minus 25 times negative 1, which is plus 25. Right? Okay. Now, I have 3 times 2, right? So I need to do a 3 by 2 box. On the top, I'll put the 3, x squared plus 2x plus 1. And then I'll put these on the side, x squared plus 25, right? And then I do each box, and I'll have my answer. X squared times x squared is x to the 4th. 2x times x squared is 2x to the 3rd. X squared times 1, that's just x squared. 25 times x squared is 25x squared. 25 times 2x is 50x. 25 times 1 is 25. And then I look for my like terms. Now, again, it's not going to be these nice diagonals. The only like terms I see here are this one and this one. So I'll bring those together, but everything else is going to live on its own. So what's the highest thing we see?
25. Oh, no, 4x.
X to the 4th, right?
Sorry, I'm confused.
And then we have plus 2x to the 3rd. We have 25x squared and another 1x squared. That's 26x squared. 50x
And then plus 25.
plus 25. And you just wrote a quartic function in standard form given only a couple of roots, right? We've come a long way. Like, we can do a lot now, right? And if you put that into Desmos, you would see 2 real roots, and that's it on the intercepts. And assume there's 2 imaginary roots. Like, we've come a long way. We learned a lot, okay? All right, so good job. Hopefully that made sense. We're going to do some more writing tomorrow, and then we're going to start reviewing for that test. And remember, no stress. Do your best. Forget the rest.